Begin by giving a brief overview of how the oil rig simulation was set up and of the components within the model. There are 4 rigs in the channel, each demanding cargo at different times. To meet this demand, types of cargo are created and immediately sent to a slip. A vessel picks up the entities and drops them off at a rig, then returns to the standby or back to the slip to load more cargo. A few of the goals we tried to accomplish through simulation of this scenario are to overall reduce cost while still delivering the demanded cargo to the correct rig in a timely manner. To accomplish this task, we needed to determine the optimal combination of ships in use. In order to control the lateness of cargo arrivals to rigs, we wanted to optimize the amount of time the ships spent waiting for cargo in the slip. In order to implement a feasible model, we had to make decisions based on open-ended aspects of the project description. Some of the main assumptions were that all cargo created was usable, entities were created one at a time and then given a quantity assignment once within the system. We also designated Slip A to only service Billy and Dan Teller rigs and Slip B to service Donnie Allen and Olympic rigs, and we omitted Slip C. When bad weather occurred, slips continued their route and were delayed at the destination. To meet demand, ships left the slips every 6 hours, even if that ship was not full. It is necessary to check that our model was running as we intended through verification. To do this, we used operational graphics, such as a status plot and labels, throughout the time we worked on the model. We also tracked particular variables, used model trace, and watched entity and ship instances. We debugged the model as errors occurred. Lastly, we matched state assignments to entities and rigs to verify that each piece of cargo was unloaded at its intended rig. We also checked that our model was behaving accurately to a real-life scenario through validation. We assumed that the provided demand schedule was accurate according to the rigs it represented. We do not have historical data or an exact real-world model to compare these constraints, so very little validation is possible. We used the sensitivity analysis tool, OptQuest, to narrow down our alternatives and determine the most cost-effective scenario. Here's an example of how we verified weather. The status labels indicate that there is good weather, therefore the boats are allowed to travel, as illustrated here in this model. Let's walk through our model. Here, you can see where the vessels come to pick up cargo from slips A and slip B. The sources creating entities for each rig are to the right of the ships. When boats reach capacity or the dwell time is met, the ships leave the slip and head for the Fortune Channel, and then to the destination rig where the entity is intended for. Now, let's watch a vessel arrive at a slip, check capacity above and below the deck, and load the entity onto the vessel. Notice all the cargo aboard a ship is of the same color. This indicates that that boat and all entities on board are headed for the same rig. Notice that this ship is a pretender. This correctly follows the constraint that pretenders can only serve the Billy rig and no other rig. We ran the model for 744 hours to simulate 1 month of oil rig operation. The graph shown shows the number of entities in the system. Some entities remain in the system when the run ends because they are demanded at the same time or just before the time the run ends. We concluded that we do not need a warm-up time due to the given arrival table. We experimented with the number of replications and chose a minimum of 400 in order to balance sampling error with our actual number of runtime in the simulation experiment, as shown by the s'more plots. To monitor how our system was performing in different situations, we created responses. Our first response gives the total cost in a month. This includes the cost of the slips, the rig shutdown cost, and the daily use of the boats. Our next response is the total hours an entity arrives late at a rig, and the rig has to shut down. The next three have to do with the time between an entity being demanded and when it reaches the rig. They record the percentage of entities that arrive at the rig in less than 24 hours, the percent that arrive between 24 and 60 hours, and the percent that arrive over 60 hours. Now let's talk about the experiments we ran on our model and the analysis that came after. First, we ran an experiment using OptQuest to test cost effectiveness. We used a binary variable investigating whether or not each ship was to be used during the month. We also tested different hours and minimum dwell time. Our experiment results showed that our as-is model was the cheapest feasible result we were given. The cheaper options were infeasible due to rigs not being attended to. Next, we experimented with having 3 ships of the same type for each rig instead of having one 200, 400, and FSB vessel. To do this, we ran a manual experiment, then used subset selection to find the lowest cost. This experiment resulted in cost savings by having 3 200-type ships service each rig, with a dwell time of 6 hours. We further experimented, but this solution proved to be the most cost-efficient, while having a low amount of overtime. Now that you've seen some of the components of our model and how they work, let's talk about our recommendations. Our analysis showed that the most cost-effective fleet should consist of 12 Type 200 vessels. The Type 200 vessel proved to be the most optimal because the capacity accommodates all entities created, unlike the Type FSB, and is more cost-effective than the Type 400 vessels. We recommend maintaining operations at Slip A and Slip B and keeping the dwell time of 6 hours to account for the standard deviation of material arrivals. The cost before these recommendations was $13,359,300. With these recommendations implemented, you should see a savings of $3 million per month at a total cost of $10,112,000.